Today we're going to jump into entropy, a part of thermodynamics that we did some thermochemistry. That probably would have occurred in first semester. This semester, we're going to talk about thermodynamics we're going to expand what we know about thermodynamics. And the material will be taken from your chapter 19. And my slides will all show chapter 17 because they come from a different textbook. But the material is the same.
Okay.
All right, so let me share the PowerPoints. And there are not that many slides, but this subject is it's difficult enough to understand as a student, but it's just as hard to teach it, especially if you're like me and you don't have the math background, because this topic really is statistical in nature. So we'll do our best. Let's see. There we go. I think Brown, chapter 19, calls it chemical thermodynamics, so that's why I gave it that title. In my book, it's a little more detailed. We're talking about spontaneous reactions, the influence of entropy on that, and the last topic is free energy. So let's try to get some perspective here. When we can visualize a chemical reaction as some kind of progress on the x-axis, and what energy changes that the system undergoes as the reaction proceeds. We've had a discussion of kinetics, which eventually led to equilibrium. But the kinetics is this part of the diagram where you can see the change in energy as it progresses over time. And this influences how fast the reaction goes. Either end, where we talk about reactants and then products, it's like this purple section is a black box. When you discuss the reaction in terms of where did it start and where did it end up, in the middle you don't care. That is thermodynamics, where you just see a state change from reactants to products. So that's where we are right now with before and after. This, I might also say that kinetics, the speed of a reaction depends upon what path the reaction takes. And that's why catalysts can speed up a reaction, because they change the path. But thermodynamics says nothing about the path. It's only concerned with the state. What state is your system in before, and what state is it afterwards? And we try to explain whether or not it's likely that that change will occur or unlikely that it will occur. So with that being said, we can predict the direction of a reaction, whether it's spontaneous in one direction. If it goes from reactants to products, and we can show that it's spontaneous this way. I should say that's not correct. That arrow on top, spontaneous. Then the other direction will be non-spontaneous. That's pretty simple. I mean, if it wants to go, and a spontaneous reaction is one that occurs without outside intervention. You don't have to force it. You just put the reactants together and the reaction goes. Now, we're not saying how fast it'll go. We're just saying that it will go. I like the example of diamond. If you take diamond in an oxidizing atmosphere like the air, and maybe a little moisture added in, thermodynamics says that that diamond will become carbon dioxide eventually. It's a spontaneous reaction. Kinetics says it's going to take millions and millions and millions of years to get there. Okay. So that's how I contrast the two. That doesn't mean that thermodynamics isn't useful. Far from it. Let's consider this example. Say we have 2.4 moles of gas, and it's in a 4-liter bulb. And there's my valve that keeps it from getting out. So we have a 4-liter volume in here, and we have 2.4 moles, and that's a gas. Okay. This bulb is connected by a valve, by that valve, to another bulb that's even bigger. So the volume here is 20 liters, but it's a vacuum. So there's nothing in it. And we're going to assume that the temperature remains constant now, and it remains constant after we open the valve, because that's what we're going to do. We're going to open that valve, and intuitively, you can probably guess that when you open that valve, what's going to happen? That gas is going to go, it's going to fill that new space. Some of it will still be here. Some of it will be over there. A lot of it will be over here. So we sort of have a feel for that. We know that's going to happen. So that would be considered a spontaneous process. Right? All you have to do is open the valve, and you don't have to force it. It's going. So in order to understand what's happening, we need to revisit some terms. What do we mean by enthalpy? Enthalpy is an expression of the potential heat exchange, or the heat change in a system. It's not the actual change, it's the potential, right? The actual change measured by heat flow is Q. They have the same units of measure, but they mean different things. Q simply measures the heat flow. Delta H says this is the maximum potential for the heat flow. And what it references is the internal energy of the system plus any changes that happen in the system relative to pressure and volume changes. So I'm going to show you a little later that if with this expression plus internal energy, if pressure doesn't change, if this term doesn't change, then this Q is equal to that value. Right, so just hold on to that till future. W, it references workflow. Well, excuse me. Delta E is internal energy. Right, that's everything. That's kinetic energy. That's potential energy contained in the bonds, or it could be any type of potential energy. It could be potential energy due to compression. If you compress a gas, it wants to get out. And if you have a piston in it and you let some of the pressure off that piston, it will expand. Well, what does that mean when it expands? Some of this may be review. But when the gas expands, this piston, right, and there's a force on it. So if we release some of that force, then there's an unbalanced force, right? The force of the gas pushing against it. If we change this force, then there's an unbalanced force, and that unbalanced force will make the piston rise until it's balanced again. And that distance that it moves here times the force that was applied to get there, this force right here, times the distance equals work. That's a definition from physics. Any force over a distance equals work. Now, there are other ways to measure work, but that is the base definition of work. And that's how we relate work by a gas on its surroundings, right? So this is the system, and these are the surroundings. So if that piston moves, then the gas is doing work on its surroundings. And the value of W in that case is negative because work is leaving the system to be done on the surroundings. So in this case, we have a negative value for W. Okay, so that defines work. And these terms, we'll revisit these terms as we proceed. Now back to the problem. I think I'll leave that there for now. Well, I erased our two bulbs. But during this expansion, and if the temperature is constant, now we're saying it's 32 degrees, which is fine. If it's constant, whatever it is. What is the delta H, delta E, Q, and W for the process you described above? Okay. Do we really have enough information? Well, there's no force resisting the movement of that gas. You open the valve and it just goes. So there's no resisting force, there's no unbalanced force to work over a distance. So there's no work being done, right? So the work, that's the easy part. W equals 0. There's no work being done. How about Q? In order for Q to happen, you have to have a change in temperature. That's the only way to measure heat transfer, is by a change in temperature. But there's no change in temperature. We just said it's constant. So Q is 0 also. Right? Well, if Q is 0, and we can't assign any change in pressure or volume, well, there is a change in pressure and volume because the gas expanded, but we don't know what it is. So we haven't realized any value change in the potential enthalpy. And the internal energy is the same as it was before. It's just spread out over more area, more volume. So all of these values are 0. So what does that mean? Well, up to this point, in fact, I've said it before, during a chemical reaction, the reactants are driven by a desire to reach a more stable arrangement. They want to be, and one way to express that is energy. So if they start out at this energy and they end up down here like that, that's desirable, right? They're more stable. Lower energy means more stability. But we don't see any of that here. I mean, not in this scenario. So we've got to find a way to explain why that process occurs spontaneously, since there's no energy change. There's no work being done. Well, there's another reason that delta H is 0 and delta E is 0. There's no temperature change. But that's also true for Q. Work is sort of a separate explanation. There's no movement against a force, so there's no work being done. But the rest of them have to do with temperature. And if the temperature is 0, then all of these values are still 0. Okay? All right. Oh, there's another explanation. Delta E, if you'll remember thermochemistry. I don't even remember. Did we talk thermochemistry? Let me look at my liquids and properties, chemical kinetics. No, we didn't. So thermochemistry is in the first semester. And we learned that in thermochemistry, the change in energy is equal to any heat flow plus any work that was done. And we just showed that neither one of those, both of them are 0. So delta E has to be 0 also. All right. So given those answers that we just came up with, they're all 0. What's the driving force for the process? Well, we had to invent something new, or not me personally, but chemists and physicists in the past had to invent some way to explain it. Right? So we had to create a new term. It's called entropy. And as it turns out, all of our explanations for spontaneous reactions up to this point, before entropy came on the scene, all of our explanations are dovetailed into discussions of thermodynamics, entropy included. So what we're developing is a more complete explanation for why spontaneous reactions occur. And we can actually quantify it eventually. We're conceptualizing right now. So this term, capital S, stands for entropy. So I guess we need to talk about what entropy is. So here are two bulbs, right, with our gas in one side and a vacuum in the other, and open it. Notice, what do you see about that? What's the difference between the images? If you have the same number of particles over here, or molecules, and you got the same number here, they got more room, don't they, to spread out, right? They're in a larger space. So maybe it's like more elbow room. This is referred to as increased entropy. When you take the same number of moles, in this case gas, and allow it to occupy more space, you have increased its entropy. Now, the definition of entropy, the strict definition, is sometimes a little hard to swallow. So we often refer to entropy as a measure of disorder. A more ordered situation would be over here, where they're all closer together. You have more disorder here. In other words, you can occupy more space, so you just spread out and do your thing. If we think of entropy first as disorder, we'll talk about other definitions in a minute. think about it as disorder, then we can view the driving force as a desire by the system to occupy more space or occupy more messy situations. Now, the problem is the second law of thermodynamics, the first law of thermodynamics, let's just go over those. All right, the first law of thermodynamics says delta E for the universe is 0. You can't create energy. You cannot destroy energy. You can only change it from one form to the other. Okay. The second law, in words, is that the entropy, the change in entropy for the universe, is always greater than 0. That is, in all the processes that are taking place in the universe, the entropy as a whole for the universe always increases. It's always greater than 0. Now, what we can do is we can isolate a system, and so that no energy, no matter, nothing crosses that boundary. And then we can talk about well, I hesitate to call it the universe. It's our own little universe in the isolated system. Then we can talk about it in terms of actually negative entropies, less than 0. But I'll hold that for a second. When we give these values, signs greater than 0, we're saying that the entropy for the defined system is increasing. Or the surroundings. We can talk about the surroundings also, how the system and the surroundings relate to one another is also a discussion of entropy. But
I'm sorry, my computer died.
Oh, okay. Did you have to get on another one?
No, I just plugged it in.
Oh, I see. It's one of those battery things, huh?
Yep.
Okay.
All right.
So the sign on the values for entropy will be positive if the entropy is increasing, and they'll be negative if the entropy is decreasing. And we can think of that in terms of disorder. Increase in disorder is positive entropy. Decrease in disorder is negative entropy. Now, I put this in bold because disorder as a concept for entropy is grossly oversimplified. Explanation for entropy. These are ways that we try to grasp the significance of entropy without putting numbers to it, because that's really the only way you can define entropy in the long run, is to quantify it. But this is useful. This idea is useful, and it can help us qualitatively assess changes. In reality, entropy is a statistical expression, and it refers to the number of possible arrangements that a system can undergo, can exist in. For instance, if we have these two bulbs with gases, and we have, let's keep it simple, let's say we have 4 molecules in there. So before we open the valve, we have these 4 molecules, A, B, C, and D. Okay, we open the valve. So what's the possibilities? Well, A could go over here. That's one possible arrangement. Or you could put A back here and you could have B here. You could do the same thing for C and D. So have 3 over here and 1 over there. So the arrangements you can have where you have 3 here and 1 over there, you can have 3 possible arrangements if you swap these out, each one like that. So you could have times 3 for these. How about 2 at a time? Well, we could take A and B over here. Right, that's 1. Or we could say C and D goes over there. Right, that's another one. So that's 1, 2. Or we could say A and D go over there. Okay, that's another arrangement. Or we could say, what if I haven't done? Oh, B and C over there. So we could, A and D could stay over here, and B and C could go over there. So that's 4. Right? So in statistical terms, this one has more possibilities. It's more probable in occurring. Or we could have 1 stays over here and 3 go over there. And you could get 3 more of those, like 1 and 3. Right? So the most probable situation is to have 2 here and 2 there, which makes sense because if these are the same size bulbs, then you're going to have equally distributed, and this will give you one pressure which will be equal to that pressure, and altogether they'd be the most probable. Okay. So these different arrangements of molecules are known as microstates. Not to be confused with a state. The particular state of a system we generally refer to as solid, liquid, gas. But a microstate refers to each individual configuration that is possible. Right? I didn't count those up right, did I? Because if you have 4 of these, you should have 6 possibilities for 2 on one side and 2 on the other. So I left a couple out. But you can have, well, I left one out here too, because you can have 4 there and 4 with this type of arrangement. You can only have 1 where they're all in one side or the other. So the most probable arrangement is the one with the most number of microstates. Right? And that number of microstates tells us that when we open that valve, they're not going to stay here like that. They're not going to go all the way over to the other side either. And they're not going to send one at a time across. They're going to equally distribute throughout. So the greatest number of microstates determines the result. Right. The beginning is one way, then the result is another way, and the result, if there are more microstates available in the result, then you will have spontaneous movement in that direction. Okay, now we can discuss entropy relative to 2 different terms. One is positional entropy, and that refers to how are the molecules actually arranged. Okay, if we say, and that's been the discussion up to this point. When we talked about microstates, we were only talking about their positions. Where are they? Right? The positional probability for their microstates. But microstate can be expressed in purely energy terms or in combination of positional and energy. But for this discussion, we look at positional. If we're looking only at position, then we say the solid has a lower entropy than the liquid, because the solid is regular arrangements, and they're generally closer together, holding occupying less volume, with a few exceptions. And the gas, of course, is way expanded into positions, right? You can take this liquid, on average, if you evaporate a liquid, it's going to occupy in the neighborhood of 1,000 times the volume of the liquid. The gas will occupy 1,000 times. Now that varies, but so that's kind of an average, which explains why an explosive like nitroglycerin, when it goes off, everything, all that liquid is converted into a gas, right? So if you have nitro in this much space, then it's going to be 1,000 times bigger in a split second, and that's where the explosive force comes from. But its entropy is what drives it. When you convert all that chemical to gas, it has the ability to occupy more variety of microstates. So the long and the short is, gas has the most entropy, liquid has the least, and solid has the least, particularly when you're talking about one substance that's making these changes. Okay, what do we mean by energy entropy? I didn't find a discussion of energy entropy in the textbook, either yours or mine. But as an independent topic, but they do make reference at some point in each chapter about a balance between positional and energy entropy. So I figure, I mean, why would they do that and not actually tell you what energy entropy was? So I'm trying to do that here. So if you consider the total randomness of a system and its surroundings, remember when we define a system, it's whatever we define it to be. Everything else is surroundings. And to simplify the whole situation, we're going to isolate. Right? So nothing crosses this barrier, not energy, not matter. So we can talk about the surroundings versus the system. Well, the total randomness of the system and the surroundings together can be described in terms of their energies. An exothermic process implies an increase in energy randomness. This energy is leaving the system, and energy randomness can be visualized in two different ways. You can have translational energy, which is kinetic, so the molecules are actually moving, or you can have vibrational, in which the molecules just sit there, and if you increase the temperature, they just get wilder until you reach a point where that activity breaks the bonds, and now you got a liquid, and that's the melting point. But that energy entropy can be used to describe the system. The energy randomness of an endothermic process generally decreases the randomness, the energy randomness. Okay, so I'm going to leave it at that for now, and we'll try to piece it back together with the rest of what we've learned in the subsequent slides. So for now, let's try to predict the sign on the change in entropy for each of the following processes. Increasing entropy will be positive, of course. Okay, so how about the evaporation of alcohol? What you have there is a liquid becoming a gas. So you can think of this in terms of positional entropy. So you have more positions available for a gas than you do for a liquid. So I would expect this value to be positive. Okay. Oh, I forgot I had this little blurb up here. The change in entropy can't be measured directly. It has to be calculated. And we'll show you how to calculate that value later. You need two terms. You need heat transfer and you need temperature. But you can also use this expression if you want to. I don't know how I would use it. My math's not good enough. This is Boltzmann's original, Ludwig Boltzmann, who put teeth into entropy. This W term, I'm not sure what that is, but it's the natural log of that W. I don't think it's work. I think it has, W is an expression of the microstates of the system. It's a statistical term. And then you have this Boltzmann constant that has to be multiplied by it in order to generate the entropy term in the proper units of measure. Okay, so we'll leave that for bigger minds. How about the freezing of water? So you're going from a liquid to a solid, getting closer together, more, well, in water, that's a bad example. The molecules are not getting closer together in the solid, they're getting further apart. But they are more regular. The crystalline structure is more regular, and that means less randomness. So the freezing of water should be a negative entropy. How about compressing an ideal gas at constant temperature? When you compress the gas, you reduce the number of microstates that it has available. You're decreasing the volume. So that entropy should also be negative. What if you heat an ideal gas at constant pressure? Well, remember, if the pressure is constant and we add temperature to it, what happens? According to Charles' law, if the pressure is constant and you heat the gas, the volume is going to increase. So if you increase the volume, you're giving the gas more microstates. And you can also think of that in terms of energy. You're increasing the energy entropy of the gas too. You're speeding up the molecules. I mean, that's why the kinetic molecular theory says that's why either the pressure increases, or if the pressure is constant, the volume increases, because those molecules now are moving faster. They have more kinetic energy. They're banging against the walls. And if one of them is movable, it's going to expand. So heating an ideal gas at constant pressure should increase the entropy. Whether you're describing it in terms of positional or energy. When you dissolve sodium chloride in water, what happens to that molecule? Well, actually, it's a crystal lattice. So what happens is the sodium chloride breaks into individual ions, which means more entropy, more randomness. They're moving into a greater space. There are more microstates available for dissolved sodium chloride than there is for the solid crystalline sodium chloride. So the entropy is going to increase. Okay. So here's a statement of the second law of thermodynamics. I think while you were going, I put that up on the board. In the very simplest terms. So this is a more elaborate explanation. So in any spontaneous process, there's always an increase in the entropy of the universe or of that isolated system. See, I want to keep up with my hard copy too. Okay. And as I said earlier, we can restrict the definition of universe. All we have to do is isolate the system and its surroundings. Then you have a universe that's more manageable. For the entire universe, I mean the real universe, no matter what you do, everything taken together, entropy always increases. So that's why they say the universe is running down. All the processes together combined, thermodynamics says that the universe is running down, which in useful terms, in practical terms, means that is less and less, we are less and less able to extract useful work from it. And there's an equation that goes with that, and we'll get to it in a few minutes, I hope, if I don't talk too long and run out of time. What we typically do is restrict the definition of universe to an isolated system surroundings, mini-universe. Okay, I already said that. The total energy of the universe is constant. We said that. So if entropy is increasing, what do you do with all that energy? Well, the energy at this point is more ordered, and the energy at this point is less ordered. So you haven't created energy, you just made it messier. Okay, so here's how we express that. The total energy of our universe, I mean, this could be interpreted as the whole universe or as our little universe. The total entropy change of our little universe is equal to the change in the system plus the change in the surroundings. Right, so if the entropy of the surroundings and the system both increase, then obviously the S is going to be huge, right? It's going to be big. But if for some reason the entropy of the system decreases and the entropy of the surroundings increases, then it depends on the magnitude as to which one, whether the total is positive or negative. We're going to look at examples of that in just a minute. Okay. For our isolated circumstances, I prefer to say the total entropy is equal to system plus surroundings. We'll get away from the use of the universe subscript. Okay. So this is just, we're going to beat this horse as often as we have to make it make sense. So the total entropy change will be positive if the system surroundings increases entropy. It'd be negative off the other direction. If, however, the delta S total is equal to 0, that means there is a tendency for the process not to occur, and that means equilibrium. Okay? All right. So let's say we have a process here, and we're going to try to dovetail the energy randomness and positional randomness together, try to make sense of it. And that's a pretty tall order, actually. So our system is such that this liquid turns to a solid. Right? So which direction involves an increase in energy randomness? Well, liquid to solid is exothermic, correct? It has to give up energy to become a solid. So in our previous understanding of stability terms, as the energy leaves that liquid to make the solid, it's more stable. So this exothermic process would be considered favoring the formation of the solid, right? And the randomness actually is decreasing. But think of it in terms of position, right? Which one, positional randomness, would favor the other way around, going from solid to liquid, because the number of microstates would be increasing from solid to liquid. So there's like a tug of war going on between the two, energy randomness versus positional randomness. Then you have to consider what's the balance between the two. Okay. All right. Now, if that wasn't weird enough, we're going to make it worse. So, as temperature increases or decreases, what takes precedence? So let's look at the scenario where temperature increases. If the temperature is increasing, positional randomness is the favorable process. So at high temperatures, positional randomness becomes more important. That's all that statement is saying. The release of energy becomes less important. Why? Because I don't know why. At high temperature, positional randomness dominates. The release of energy becomes less important. So I think what the idea here is, if you release 1,000 joules during a process at 1,000 degrees Kelvin versus 10 degrees Kelvin, on a percentage basis, what is that going to matter? If you're at 1,000 degrees, a kilojoule means nothing. But if you're at 10 degrees Kelvin, 1,000 joule change is going to make a huge difference in the entropy of the system, the randomness of the system. So I think that's what's being meant by here. High temperature, the positional randomness dominates. That is, how many microstates do you have in terms of position at high temperature? As temperature decreases, the energy randomness, it becomes the more favored process for determining the entropy for the total. And positional randomness becomes less important because the molecules, they're not moving very much. They don't care about going anywhere. So let's say that again. At high temperatures, positional randomness is the dominant process. At low temperature, energy randomness is the dominant. Okay? So at what temperature is there a balance between these two, energy randomness and positional randomness? Well, for the phase change of a liquid and a solid, that balance occurs at the melting point. So what if we apply it to other types of changes? Let's see if we can describe spontaneous, non-spontaneous, or we just don't know, relative to these different scenarios. So a reaction that is exothermic but becomes more positionally random. Let's see, if it's exothermic, let's see. Oh, okay, here we go. If it's exothermic, we're saying that the energy, remember that change from liquid to liquid and solid in the previous slide. Let's go back. Here we go. There we go. Exothermic favors the formation of the solid. There we go. An exothermic reaction favors the formation of solid. And if the system then becomes, well, it doesn't have to form a solid in this case. It just says it's exothermic. So it could still be a gas. But we're losing energy. We're losing that energy randomness. But in the process, we're also becoming more positionally random. We find that that is a spontaneous system. And I don't know about this. Both driving forces are favorable. I thought exothermic was the other way around. All right, let's look at the rest of them and see if they start to make sense. I'm still hold my doubts there. Exothermic, but becomes less positionally random. In this case, we can't tell. We're saying that exothermic is favorable. Well, okay. We can say it's spontaneous. Exothermic is a driving force. Randomness, positional randomness is also a driving force. So if you've got both of those processes going on at the same time, the system should be, the process should be spontaneous. Okay, now that makes sense to me. Exothermic says spontaneous. Positional randomness increase says spontaneous. Both of them together say spontaneous. But if exothermic is against less positional randomness, then it depends on which one's bigger than the other, which one dominates, right? And what do we say about positional randomness? That dominates at high temperature. So an exothermic process at high temperature should be spontaneous. The other way around, endothermic means that's not a driving force, but this is a driving force. So this one would become spontaneous at low temperature. And of course, if you have endothermic and less positional random, that's not spontaneous no matter what the situation. I think it'll make more sense once we put it into a formula. And we're headed there, believe me. So this first one and the last one are not affected by temperature, but the two in the middle are affected by temperature. Okay, let's speak in terms of we have our isolated situation, and we have a system, and we have surroundings. Right? And it's isolated. Okay. Now let's look at the entropy of the surroundings only. The sign of delta S for the surroundings depends on the direction that heat flows. If heat leaves the system, right, this way, that means Q is negative because everything is referenced to the system. Or in limited circumstances, we can also refer to it as negative delta H. As heat leaves the system, randomness in the surroundings increases. Right? Because this is exothermic process for the system, which is negative here, but it's adding energy randomness to the surroundings. Okay, what if heat enters the system? Then the randomness in the surroundings decreases, and the delta H is positive. So, and the magnitude of the entropy change in the surroundings depends on the temperature, right? If this movement of heat is accompanied by a huge change in temperature, then you're going to have a massive, well, let's see. No, I'm sorry, it's the other way around, because high temperatures favor randomness over temperature, over heat, or energy randomness. At high temperatures, we're referencing positional randomness. But delta S does depend upon the temperature. And of course, I mean, it's obvious. The delta S is a difference, right? So the difference is going to be greater if the surroundings are at a lower entropy to start with. What we're saying in so many words is that the delta S for the surroundings is directly proportional to the heat transferred, right? You transfer heat, increases, direct proportion. But it's inversely proportional to the temperature, simply because of the effect the temperature has on the entropy change, right? If the temperature is very, very, very low, then the entropy change is going to be more significant. So how do you express that as a direct versus indirect? Well, the delta S then for the surroundings would be proportional to the heat transfer and inversely proportional to the temperature. Now, in order to make the signs come out right, this, since we're talking about the surroundings, and this is in reference to the system, negative here, this should be a negative Q divided by T, simply because we have to change the sign to express it in terms of the surroundings rather than in terms of the system. So here it is in words. The magnitude of the entropy change is proportional to the heat and inversely proportional to the temperature. So in an exothermic process, going this way, let's see. I thought that was supposed to have a negative sign. Yeah, it is. The change in the surroundings is the quantity of heat transferred to the surroundings divided by the temperature. In an endothermic, it's the other way around. The surroundings are losing energy as a quantity of heat, and that's also proportional to temperature. So here is the formula. I said Q there. Since this is a potential, and if we hold the pressure constant, then this is true. The entropy change of the surroundings in a process is proportional to the negative of the enthalpy and inversely proportional to the temperature. So surroundings minus delta H over T. Oh, and this is my explanation. I said that if pressure is constant, then the delta H equals Q. Well, here's the proof. These are different values, enthalpy and Q. Q is an actual measure of heat transferred based on temperature difference, whereas enthalpy is more of a potential change in heat energy. Okay, it's essentially a measure of the potential energy of the system. And enthalpy is defined by this equation. Don't ask me where it came from, but it's true. the enthalpy or the potential energy of the system is its total energy plus any changes that occur in pressure times volume. Right? So what is delta E equal to? We've already shown that delta E is equal to Q plus W. So this term right here is delta E. Notice it's equal to that, delta E. Q plus W equals delta E. So if we substitute it in and let the pressure be constant. So we take this delta sign, instead of letting pressure change at all, we say the only thing that can change is volume. Pressure has to stay the same. So we put the delta on the inside next to volume. Okay. Next step. We know that from thermochemistry that the work is equal to the negative pressure times the change in volume. Right? At least I showed my first semester class that. But it's true. So if we substitute this for W in here, then we get delta H equals Q minus P delta V plus P delta V. Those cancel. And in that case, delta H equals Q. That's why most experiments in chemistry, unless you absolutely have to let the pressure change, you hold the pressure constant during the process. And that way you can measure the Q and infer the enthalpy from that value. Okay. All right, so here we have a situation. Several situations, actually. And we're going to use that relationship. Okay, in this slide, it's got delta S for the universe, which means total. I mean, not the big universe, but delta S total. Okay. So I don't need to put that on the board, as long as I explain that that means total and not universe. Okay, is the process going to be spontaneous? Remember that delta S for the system plus delta S for the surroundings equals delta S for the universe. So there should be an equal sign right here. All right, if the change in entropy for the system is positive and it's also positive for the surroundings, then you have a spontaneous system all the time, no matter what the circumstances are. If, however, they're all negative, then you have no spontaneity. The reaction will not occur in the direction given, from left to right, right? From here to here. That's non-spontaneous. But it also says that in the reverse direction, it is spontaneous. So you don't have to get down in the mouth if you see that your reaction is listed as and you determine that it's non-spontaneous, because it also tells you that the other direction is spontaneous. Okay. In this case, where the system has a positive entropy change and the surroundings have a negative entropy change, the spontaneity depends on whether or not the system entropy is larger in magnitude than the surroundings. And that just makes sense. If you subtract some of this from that, then if they're equal, actually, then you've got equilibrium, because delta S is 0. But if this is large enough and it's positive here, then you have a spontaneous situation. Vice versa, if the delta S for the surroundings is positive and that for the system is negative, then it's only spontaneous if the surroundings entropy is large enough to offset the delta S for the system. All right. So let me see here. What's next? Now we're going to get to something we can really sink our teeth into. This person, Josiah Willard Gibbs, was an American, and he was working on this problem in the, I don't remember when he lived. I think he kind of transitioned from 19th to 20th century. But he was concerned with, all right, we know energy can be generated from a spontaneous process. And he wants to know how much of that is available to do useful work, right? Because everybody knew at that time that you never got all the energy back that you put in. Like if you put in energy to create a compound and then you react it in reverse, for some reason you never get it all back. So he wanted to know, all right, how much of that energy that I get back is useful? How much can do work? So he created this concept, and this is not the only one, but it's the most popular one that's used, is the Gibbs free energy. Right? So a change in energy, and obviously that change in energy is going to be in joules. And of course, delta H is in joules. And this term, minus T delta S, is going to be joules also. How do I know that? Because delta S units are joules per K, right? Delta S, for the surroundings anyway, is minus delta H over T. This is joules, and that's K, right? So if you put that into the formula, this is going to be joules K. This is going to be K, which cancels that. That leaves joules. This is joules. That's joules. So dimensional analysis tells us that the units are correct. Yeah, word of warning. Most chemical reactions are listed as kilojoules, and most entropy values in reference manuals are in joules, not kilojoules. So when you stick them into this formula, be sure you've got the same units of measure. Either change the delta H and the delta G to joules from kilojoules, or change the delta S to kilojoules. But they have to be the same units. All right. Whenever we say, whenever there's no subscript here, we're talking about the system. We're talking about that little defined area here, surroundings everywhere else. All right. So what does this actually mean? Well, the Gibbs free energy is the amount of work that can be done. It's related to the work. And remember, work can be expressed in joules also. So they're equivalent. So the amount of energy that you get here can be used to do that much work as a maximum. And even that will suffer some losses. But it's not the same losses as experienced in this part of the equation. Right? So this is the potential available energy, but it loses something in this entropy change. And when you subtract out that entropy change, then you find out how much energy is actually available to do work. Okay. We can relate the total entropy change, that is surroundings plus system, to delta G. What we have to do is set that value equal to this term. And this occurs at constant temperature and pressure. That's the only way this works. Once you know the delta G value, and you know the temperature at which it occurs, then you can calculate the entropy for the entire system. Okay. Just keep that in mind. So what that means, and one of the purposes of this formula is that if delta S total is positive, right? We already said that means spontaneous. But if that is equal to negative delta G over T, then if this is positive, what does delta G have to be? A negative, negative, right? So if delta G is negative, that's spontaneous also. That's just so we can get a handle on the signs of the numbers. If this one's positive, total, it's spontaneous. But also, if this one is negative, it's spontaneous. Okay. So all that is saying is that as free energy decreases, if free energy decreases, that means that the process that it describes is a spontaneous one. So remember this one, right? We looked at that one just a few minutes ago. Delta S for the surroundings is minus delta H over T. All right, just hold on to that for a while. I have a suspicion we're going to come back to it anyway. And let's look at a liquid that vaporizes at its boiling point. All right, so what would be W in that case? If it vaporizes, now this is assuming that as it vaporizes, we can extract a force over a distance. Right? If you can do that, then vaporizing a liquid means that the gas is doing work on the surroundings as it expands. It's pushing against the surroundings, and that's a force over a distance means, and the value of that work is negative because it's leaving the system. If you're vaporizing the liquid, then you have to add energy to it, correct? That means that the system is gaining energy. Heat is required. Well, what about delta H? Well, it depends. Since it's related to this heat transfer, they may not be exactly equal, but the delta H will be positive because you're adding heat to the system. All right, how about the entropy of the system? You're adding heat to it and the gas is expanding. So I would say the system is a positive delta S. The gas is more disordered than liquid. That's one way of thinking of it. How about the surroundings? What's happening to the surroundings? The surroundings, the entropy is decreasing. It's becoming more ordered because we're extracting heat from the surroundings to accomplish the vaporization of the liquid. And the only way that the surroundings can do that, if the temperature is constant, is that they have to become more ordered as they release energy. So the entropy for the surroundings would be negative. All right, how about delta G? Well, as it turns out, at the boiling point of a system, delta G is 0. There's no useful work to be obtained. Okay. And if delta H equals the temperature times delta S, and that should be, was that from a previous equation? Well, let me look here in my hard copy before I flip slides. Yeah. If we take that delta H, delta S equals minus delta H over T, and we solve it for this one, right? The T then becomes a multiplier of delta S. And then we substitute. We find that if these two are equal in magnitude, but opposite in value, then we find that summation equals 0. That's what we're getting at there. And that occurs at the boiling point. It's only when you are below the boiling point, or you've boiled everything off and now you've got complete vapor, that Gibbs free energy can be either positive or negative. Okay. So let's try to work a problem, if at all possible. Let's see. I'm not on the screen yet. Let me see here. Yeah, let's move this over just a little bit. There we go. So the value of delta H for vaporization of a liquid, which we call X, is 45.7 kilojoules per mole. So the delta H of vaporization equals 45.7 kilojoules per mole. All right. And its normal boiling point is 72.5 degrees. So the temperature for the boiling point, and that's normal boiling point, which means 1 atmosphere pressure. Right. Well, we say that down here also, 1 atmosphere, is 72.5 degrees C. Okay. Calculate the entropy change for the system, the entropy change for the surroundings, and the delta G for the vaporization of 1 mole of this substance. Okay, so well, where do we start? We start from where we left the last slide. If we're at the boiling point, delta G has to be equal to 0. Right? Delta G is equal to 0. Okay. What's next? Well, we know that the surroundings can be calculated from minus delta H divided by T. So the T has to be converted to K. Let's see, can I do that in my head? Let's see, 3, 5, 345.5 K. And we divide that into the number of joules, right? So this would be, and when I convert kilojoules to joules, I just take that term, that K right there, 1,000 times right? And that makes it joules per mole, 45.7 times 10 to the third. Or, and that's the way I did it here, of course. So negative that term divided by the temperature gives you minus 132 joules per K mole. Okay. So at equilibrium, the total entropy change should be equal to 0. And that's what we've got here. The boiling point is an equilibrium situation. So at equilibrium, these two are going to be equal and opposite in sign. So that means the system has to be the same magnitude, but opposite sign. Okay? Oh, I got a video. Let's see. 222. It'll take about 8 minutes. And then I've still got to talk about, well, I think this will be good. It'll pull everything together. So let's go ahead and watch it. You might have to turn up your volume a little bit.
Professor Dave here. Let's learn the laws of thermodynamics.
He knows a lot about the science stuff. Professor Dave explains.
The laws of thermodynamics help us understand why energy flows in certain directions and in certain ways. A lot of the concepts described by thermodynamics seem like common sense, but there is a layer of math beneath the intuitive level that makes them very powerful at describing systems and making predictions. We won't get into the math, but we should be able to describe these laws conceptually. The first law, described in the most basic way, highlights conservation of energy. Energy is not created or destroyed, it only changes forms, from potential energy to kinetic energy to heat energy, etc. While we have found this to be untrue on the quantum level, for chemists it does just fine. However, there seems to be a preferred direction in which energy flows from one form to another. In order to understand why, we look at the second law. The second law introduces a new concept, entropy. Entropy is quite difficult to understand, so we can most easily describe entropy as disorder.
Hello.
And the second law states that the sum of the entropies of a system and its surroundings must always increase. In other words, the entropy or the disorder of the universe is always increasing. Within a system, there is also a tendency to go towards higher entropy. The classic analogy is that your bedroom will over time become messy, but it won't suddenly become neat. Another way to look at this is to say that entropy is a measure of how dispersed the energy of the system is amongst the ways that system can contain energy. Yet another way is to analogize entropic states to computer code. Let's take, for example, an ionic solid compared to the same substance as a liquid. Clearly, the solid state is more ordered and the liquid state is more disordered or higher in entropy. To describe the solid state using computer code, you would need to include terms that describe the geometry of the lattice, the intermolecular distances, the precise configuration of every molecule, and many other things. But to describe the liquid state, you would need to simply describe the volume of liquid and the shape of the vessel, because the motion and configuration of the molecules are random. That's far less information that needs encoding, which is a way of rationalizing why increasing the entropy of a system is thermodynamically favorable. We can look at all kinds of processes to highlight entropic influence. Heat will flow from a hot coffee cup into the table or your hand because the heat energy will be more disordered if more dispersed. This is why heat spontaneously flows from hot to cold and not the other way around, entropy. The third law states that a perfectly crystalline solid at absolute zero has an entropy of zero, as this is the most ordered state the substance can be in. Entropy is measured in joules per Kelvin. Note that entropy is not a measure of energy itself, but of how energy is distributed within a system. It is enthalpy, the thermodynamic quantity we learned about before, that is more accurately describing the energy of a system. As we will see, enthalpy and entropy intricately relate to tell us something about the Gibbs free energy of a system. G, or Gibbs free energy, tells us whether a process will be spontaneous or not, meaning if it will simply happen on its own. Change in Gibbs free energy is given by this equation, which includes change in enthalpy, change in entropy, and temperature. If delta G is negative, the process is spontaneous. If positive, it is non-spontaneous. So we can use this equation to see how a spontaneous process can be either enthalpically or entropically favorable, or both, but not neither. For example, if delta H is negative, which means exothermic and energetically favorable, and delta S is positive, which means an increase in entropy, which is also favorable, a negative minus a positive will always be negative, or spontaneous. If the opposite is true, and both are unfavorable, we have a positive minus a negative, which will always be positive, or non-spontaneous. If only one of the two is favorable, we have to do some math. If delta H is positive or endothermic, that energetic unfavorability could be outweighed by the other term if the process is entropically favorable. And since T is here, this factor will increase with a larger T. So entropically favorable processes are more likely to be spontaneous at higher temperatures. Conversely, if it is energetically favorable but entropically unfavorable, the entropic unfavorability will be minimized at lower temperatures. This is a very important equation to understand because it describes all of the spontaneous processes in the universe. There are those who incorrectly use entropy and the second law of thermodynamics to imply that order can't happen spontaneously. But we just showed that entropically unfavorable processes can be spontaneous at lower temperatures if they are energetically favorable. An example of this is soap. You need soap to wash non-polar dirt and grime off your hands because they are immiscible with polar water molecules. But soap molecules have polar heads and long non-polar tails, which allows them to spontaneously form structures called micelles. These are spheres where the soap molecules orient themselves with the polar heads facing out in order to maximize ion-dipole interactions with water molecules that bring the system to a lower energy. And the non-polar tails will all face in, trapping the dirt by making a network of van der Waals interactions. The dirt trapped in the micelles washes away because the micelle as a whole is water soluble due to the polar heads facing out. That's how soap works. And that's also how highly ordered structures can form spontaneously if by enthalpically favorable or energy storing processes. In this way, systems can defy entropy on the small scale, but the second law does hold true in that the entropy of the universe is always increasing. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
All right.
Professor.
Okay. So that was kind of a, and sometimes it's good to have somebody else explain these things. You hear it in different terms from another mouth. Sometimes it's helpful. I hope it was anyway. So when we have, and this table is an expression, another way of putting the information that Professor Dave gave us, where you have, if the delta H is negative and the delta S is positive, then you get a negative and a negative times a positive, which makes negative, which means it doesn't matter what the temperature is. This situation always produces a spontaneous reaction. Whereas if they're both, if delta S is positive and delta H is, well, let's look down here. Oh, if delta S is negative and delta H is positive, then you get a positive value no matter what. So delta G being positive means this reaction is not spontaneous at any temperature, but it is spontaneous at all temperatures in reverse. Okay, the other two situations where you have both delta S and delta H positive are delta S and delta H negative. The positive implies that the spontaneity occurs at high temperatures only. Because with the delta S positive, you need a high negative value of this term in order to offset the positive value of the delta H. Whereas if the delta H is negative and the delta S is also negative, then you need a small t, because it's going to give you a positive value added to a negative, and you want to maintain the total here as negative to be spontaneous. So that only occurs when the temperature is low. All right. Let's see. Do I want to spend time on this? Yeah, we probably ought to. I'll just go over time if necessary. Gas A2, so that's a diatomic molecule, reacts with gas B2 to form gas AB at constant temperature and pressure. So that would look like this. There you go. The bond energy of AB is much greater than that of either reactant. Right? So what that says is that you have released energy. If the bond energy here is lower than it is for the summation of these two, that means you lost energy in the process. This is more stable, and energy was exothermic, right? So what's the sign of delta H? It has to be negative. There it is, negative. How about delta S for the surroundings? Well, if delta H is negative, it's negative delta H over T. So delta S for the surroundings would be positive. There. How about for the system? We can't really tell. If we're at an equilibrium situation where delta G is 0, then the delta S surroundings and delta H systems would be equal to one another. But we don't know. We could say it's approximately 0, but we don't know the exact value. And the delta S total then should be positive. Okay. Oh, and this equation I stuck up here, this is one that we've used before, where you determine the delta H by adding up all the bonds that were broken and formed. We did that one in a previous chapter. All right, so Professor Dave mentioned the third law of thermodynamics. The entropy of a perfect crystal at 0K is 0. And the entropy of a substance, what that means is that entropies of any substance that you choose to identify, whether it's an element or a compound, the entropy compared to that 0 point is always positive. It's like the temperature K is always positive. Entropy is always positive. So remember when we were doing thermochemistry and we were adding up enthalpies of formation for each of the reactants and products in order to get the delta H for the entire process. The delta H for any element was 0 in its standard state. But if you do the same thing for enthalpy, entropy, delta S, entropy, every term in your reaction will have a value, will have a positive value. So if you want to calculate the standard entropy for components in a reaction, reactants and products, you add up the products and you subtract the reactants, just like we did for enthalpy. Only in this case, every term will have a value. You won't have any zeros in there. So if we do it for this one, we need to add up the entropy for this term, right? So it's right here, times 2, right? So that's 100. And then H2 will be 131. So that's 231. For the products, now let's subtract the reactants. Okay, sodium, 51 times 2 is 102. And then 2 times water is 140. So that's 242, right? So that's a negative 11, right? That's joules per K mole. All right. There are also standard free energies. But in the case of standard free energies, you do have values equal to 0, just like delta H. And you add up the products and subtract the reactants, just like you would for delta H or delta S. So what does that mean for this equation right here? Right? If you can calculate this one and that one, and you know the temperature, you can find out what delta S is here, right? So you don't need that Boltzmann's equation to find delta S. Or if you happen to know the temperature in delta S, and you know the free energy, you can find out what the enthalpy is for that reaction. So it's like any equation. If you've got one unknown, you can solve for it. Let's say a stable diatomic molecule spontaneously forms from its atoms. So we're saying it's spontaneous in this direction, and you form the diatomic from the atoms. Predict the signs of delta H. Well, delta H tends to be negative, right? The enthalpy is giving up energy. As these two lone atoms come together, they're going to give up energy. So the delta H should be negative. Oh, gave them all to you, right? What's delta S? Well, you're going from 2 moles of atoms to 1 mole of product. That's a decrease in randomness. And then if you delta G, we say it's spontaneous. We don't need to know what these values are in this case because we're told that it's spontaneous. So they're all negative. Okay? Actually, I work backwards. That one's spontaneous, it's negative, right? We're given that. You go from 2 atoms to 1 molecule, delta S is decreasing. You lower the energy of the separate atoms by bringing them together in a bond. So they're all negative. How about this one? Let's see. Am I getting close? We're getting there. I got a little more time left. Okay, so let's look at this one. We have a system. and the system is the reaction. One second. Hello? I want to talk to Lori. Okay. One more second. I need to check something. We've got a reaction that's taking place at constant temperature, 25 degrees, and it's phosphorus trichloride plus chlorine gas yields phosphorus pentachloride. And the delta G is minus 92.50 kilojoules. All right. We know this reaction with a negative delta G equal to, delta G equal to a negative 92.50 kilojoules, that is spontaneous. That's not the question. That's just given information. The question is, what will happen to the ratio of partial pressures of PCl5 to the partial pressure of PCl3 if the temperature is raised? Right, so we're saying we're at equilibrium at 25 degrees. All right, so what's going to happen if we raise the temperature? What happens to the ratio of PCl5 to PCl3? Partial pressures. Right? So there's the partial pressure, there's the partial pressure. What's the ratio of those two? Right? So we can use this expression, and I thought I had an I do have an explanation. Delta S, what happens to delta S in this case? Look, you're going from 1 mole here, 1 mole there, 1 mole there. You're going from 2 moles to 1 mole. So delta S has to be negative. Right? You're going from 2 moles to 1 mole. But the reaction is spontaneous. Right? So what does that mean about delta H? If this is negative, hello? Delta G equals delta H minus T delta S. So if this one's negative, and this one is negative, that makes this term positive, right? Then at this temperature, 25 degrees, delta H must be negative. It's exothermic. Right? If that's negative and this is positive, then the only way that this one can be negative is for delta H to also be negative. And it has to be larger than that value. Right? So delta H must be negative. Okay, so what does that mean for the ratio? If we raise the temperature. If we raise the temperature, we make this one more and more positive, which makes delta G less and less negative. So what that does is it means the reaction is not as favorable. It becomes less and less favorable as delta G decreases. Okay, as delta G decreases, that means you have less of this on that side and more of this on this side. Okay, and that being said, now the ratio between these two is decreasing. I hope that made sense.
It did.
Okay. We can also infer, let's see. We can also infer that if delta H is negative, we're giving up energy. We can use Le Chatelier also. So if it's exothermic, now that we've determined it's exothermic, we can put our enthalpy on that side. So now if we increase the temperature, we're adding this component, which drives the reaction backwards, makes less of that and more of this. And that also will give you the same answer. Okay. So what if our system surroundings is not at equilibrium? And we want to determine what is the delta G under those conditions, right? So if we have a non-equilibrium equation, right, where we're given so much of this and so much of that, and maybe even so much of that, and we determine that it's not equilibrium, how do we do that? Well, you do the Q value and you compare it to the K, and that'll tell you whether it's at equilibrium or not. But what we want to do is determine what is the actual delta G, not what's the standard, right? Because most reactions don't occur under standard conditions. So what we want to do is take the delta G that we know, standard, and then use this correction factor to determine the delta G. If we know the P, and this is in terms of, excuse me, and this is in terms of pressure values. Then we can do it for gases. If we know the Q in terms of concentrations of various solutes, then we can use this expression to give us the delta G. Okay. So it depends on the units, whether you have pressure or concentrations. All right. The point of this illustration is to emphasize the fact that delta G for a chemical reaction gives you the lowest possible free energy if the system is at equilibrium. If it goes to completion, then it's over, right? There's no free energy minimum that can be reached. So if this A goes all the way to B and rides off the end of the ramp, that reaction is complete. But if you go down to here and you wobble back and forth, you end up at C. Then you're at the lowest possible free energy for that reaction. And you can also say that you're at equilibrium. So what does that mean in terms of delta G? Well, the delta G under standard conditions might be one value, but the delta G at equilibrium, the actual delta G at equilibrium is 0. Once you reach equilibrium, then you cannot, under those conditions, extract any more energy from it. You can't do any more work. So that means that the delta G here, under these conditions, is 0. And then that is also equal to delta G under standard conditions plus this correction factor. And if you're at equilibrium, then that Q actually is K, right? Because K is the equilibrium expression for the system. All right. Only if you've got a Q in here, a non-equilibrium situation, can you calculate a non-zero value for G. But if you're at equilibrium, that's not a bad thing. Now, if you know the K for your equilibrium system, you can calculate the delta G, right? You just put the delta G on the other side and leave the negative behind. So now this delta G has no sign, but this expression has a sign. And all you have to do is plug in your K value under standard conditions, and you can calculate the delta G 0. Right? So that's what's good about equilibrium. Or if you know the delta G, for some reason you can calculate that, then you can figure the K. Now, it's important to recognize that this R is not the same R that we used with gases, right? The R that we used for gases was 0.08206, and that was liter atmospheres per mole K. This R value, since energy is involved, we use a different R value. And I'm scratching my head. 8.415 maybe, something like that, is joules per mole K. So you've got to use the right constant there with the energy factor in it. All right. So, oh, I skipped a slide. Here we go. What's the change in free energy to reach equilibrium? Well, if equilibrium is in that trough, and the position for equilibrium in terms of free energy is here, then you could come at it from this direction, or you could come at it from that direction. And the fraction of A, and I assume what they're doing is they're going back to 2A's yields A sub 2. Then this gives you the equilibrium position. I'm not sure what the value of that is. Let me go to the next slide. Maybe it'll make sense. All right. If the standard delta G is equal to minus RT log natural log K, then what does that mean for K related to delta G? Well, if K is equal to 1, then delta G 0 is equal to 0. Right? It has no, it's not spontaneous under standard conditions. Because what's the natural log of 1? Well, e to what power equals 1? 0. So if the log of K, log of 1 is 0, then the whole expression is 0. If K happens to be large, greater than 1, then what happens to delta G? Well, if it's greater than 1, that means products are favored, correct? Products are favored. So greater than 1 means that the overall expression is negative. And that means delta G is negative. And that reaction is spontaneous. Whereas if K is less than 1, then we plug less than 1 value in here, we get a negative. And a negative times a negative is a positive and delta G is positive, and that means it's not spontaneous under standard conditions. Now, that doesn't mean you can't make the reaction spontaneous. Right? All you have to do is change the conditions temperature-wise is the way you would go. Change the temperature so that the K now is greater than 1. And then the reaction becomes spontaneous. Okay, so here's the equivalence next to the last slide. Here's the equivalence of work and free energy, right? This is what Gibbs was getting at the very beginning. You know, what's the maximum amount of work you can obtain from a process, and how do you express that? Well, he found that that expression gave him the delta G, right? And this doesn't have to be at standard conditions. This is just any delta G is equal to the maximum amount of work that can be obtained from any process. So if delta G is negative, then W is going to be negative, right? And that means the system is doing work on its surroundings. Okay. The one caveat to all this maximum amount of work that's obtainable see, am I still on getting there? There we go. So let me erase this first, and then I'll finish my sentence. Okay. So the maximum amount of work that's available from a spontaneous reaction requires that the process be reversible. So in order for you to extract the maximum amount of energy from the process, you have to be able to go backwards by the same path. Let's say A equals C. Now, if you do this on a large scale, that will never happen. But if you do it in increments, if you do it in small bits, with small amounts, over small amounts of time, and small exchanges of energy, then theoretically, you can reverse the process. And only under those conditions where this is reversible are you able to extract the maximum amount of energy. So what does that mean in practical terms? It means that real world reactions from which you want to extract energy are never 100% efficient. They will never give you all of that free energy. So you're losing from this potential, you're losing that much right there to give you this one. And that's equal to the maximum work. But once you get here, you'll always get less out of it than that. That's just the maximum, right? The holy grail, as it were, for instance, the internal combustion engine, right? We've got versions of the internal combustion engine now that are pushing 50% efficiency, right? That may not seem like much, but based on this maximum amount of useful energy that can be obtained from the combustion of octane in your engine, but it is an improvement. Okay, and from a practical standpoint, if we had to make all of our reactions reversible, then the world would move at a snail's pace, because you could only get tiny amounts of energy at any one time, and we just can't operate that way. So this is all theoretical. And you need the theory. You need to know what the target is. You're shooting for this much. But you've only managed between 35 and 50% now. All right, so the short version of what I just said was all real processes are irreversible. You go one direction, that's it. The only way you can get back is by a different process, and you have to force it. In other words, in order to get back this way, if this is spontaneous, the only way to get back is to couple that reaction with some other process that is more spontaneous than this one is. It has to be more spontaneous because you're going to lose some in the process, and you need a minimum amount to get it to go backwards. So that's how air conditioners work, right? You would expect heat to move from high temperature to low temperature. So in the summer, the spontaneous process is for heat to come into your house and make it unlivable. So we use air conditioning. Well, in order to do that, we couple a process, the evaporation of a gas, to extract energy from the air and reverse its entropy, right? Air, as it gets warmer, obtains more entropy. Obtains more entropy with heat increase. So if you extract heat, you reverse the entropy drive. So that's the only way that you can get a process to reverse, is to couple it with one that's more spontaneous than the one you want to reverse. Okay, I thought these were funny. This is one way of expressing the first law of thermodynamics. You can't win, right? Energy in the universe change is zero. Delta E is zero, right? So you can't win. By win, we mean you can't get something from nothing. You can only break even. Okay, can't get more energy out than you put in. Then the second law comes along and says, okay, you can't even break even. That's because in the process, you lose to entropy. Any transfer of energy will waste some to entropy at the minimum. And then the third law says, you can't even get out of the game. In other words, if you can't win and you can't even break even, then why play? Too bad. You're stuck. You can't get out of the game. And the only way to extract maximum, all the energy that is available, is to couple whatever process you have to absolute zero. And we're never going to get to absolute zero. Why? Well, how do we decrease the temperature of something? We take this one and we put it right up against this one. This one's warm, this one's cold. So heat transfers from warm to cold, right? So if you're trying to get this one down to 0 K, what can you couple this with that's colder than 0 K? Nothing. That's why you're never going to get to 0 K, because you can't transfer. All right. So that was a lesson in futility. Now, there's some scientists who have claimed that they have reached 0 K. And they do it for one molecule at a time. So what they do is they have these gas molecules, and they fire lasers at them. And if you hit them just right, you provide enough energy to stop them right there. Immediately, they stop. And that theoretically is 0 K. They have no energy. They're not vibrating. They're not traveling in any direction, so they have 0 K. So I guess technically you can get there, but you don't get there by heat transfer. So what's the moral of this whole shebang? If you're going to use energy, you always degrade it. It becomes less useful when you use it. That's it.